All right, so let's work an example for a steel column, okay? Often the same shapes that are used for flexure, that being like I-beams, a lot of times those same shapes might be used for cases where they're carrying axial compressive load. And so that's what we're going to look at today. The specific cross-section that we're going to be looking at is a W6 by 20 cross-section that is 12 feet long. And this is kind of interesting with a lot of these column problems. They sometimes just give you sort of a textual description like this of what's going on. So we're going to try to figure out for this kind of cross-section and that length, we're going to try to figure out how much maximum allowable centric compressive load this column can carry when the column is unsupported except at its ends. That's essentially saying there's no additional kind of support schemes that are happening that are going to increase the amount of, buckling load that it might be able to carry. And we're going to kind of run through a few different kinds of additional constraints that we're thinking about for each of these things. So the first one I'm going to say is, what if the column is composed of A992 steel? What if it has pinned ends and can be analyzed using Euler's equation? So let's say that, we're saying, what if we just plain old use Euler's equation? We know what this steel is, A992 steel, has pinned ends. So let's just kind of, get started with this. The critical buckling stress equation is pi squared times the elastic modulus. This is as long as we are in kind of the range of the curve that is, for Euler's equation. So pi squared times the elastic modulus over the effective slenderness ratio squared. And just as a reminder, the effective slenderness ratio is KL over R, where L is the length of the column, R is the radius of gyration for the column around the weaker axis, and K is the effective length factor. Okay, so let's first look at column length, right? Column length is 12 feet, so that one's easy. What about radius of gyration? Okay, what I want to show you here is that when you look up one of these kind of standard cross-section beams, right, standard cross-section steel shapes like this one of the things that you will find in the entry is that there is a column for R, right? And they give you R around, for a section where you are flexing it around the XX axis. Notice this is XX right here. And around the YY axis as well. It means a different color there, right? Around the YY axis, right? We have another R for that. Which of these two R's should we be using when we're finding our effective slenderness ratio if we're not given any other constraints? You want to look for the one that has a smaller R value, right? Because that is the weaker axis. It's going to lead to a smaller I value, right? You'll both find that the R value as well as the I value are both going to be smaller. And for one of these I shapes, you can always suspect that that's going to happen around the axis that essentially passes through the web of the I section, right? So what I'm going to say here is that for this beam, our R value is going to be 1.5, okay? And so with that R value of 1.5, a length of 12 feet, what about the effective length factor? Okay, this is a reminder over here. When we have different kinds of end constraints, both ends pinned leads to a K value of 1. One end pinned, one end fixed gives you a K value of 0.7. Both ends fixed gives you 0.5. One end fixed, one end free gives you 2. Okay, so what do we have for this question that we're trying to solve right here? Okay. So we have an ESR, which is going to be equal to, right, K of 1, L of 12 feet, and an R value of 1.5 inches. Now, what do I need to do with this equation to actually kind of turn it into a pure ratio? 12 inches per foot, right? I got to get rid of those feet and turn it into inches. And once I do this, it ends up telling me that my effective slenderness ratio for this one is going to be equal to 96. All right, now what? My critical buckling load, right, or excuse me, critical buckling stress is going to be equal to pi squared. What's my E value for an A992 steel? Without taking the time to look it up, it actually has the same E value as the E value for A36 steel. Some of you might remember this one. It is 29 times 10 to the third KSI is the E value. This is all now going to be divided by the effective slenderness ratio of 96, that value squared, and this ends up giving me a critical buckling stress of 31.057 KSI. So my next question is that what we were looking for? Technically what we're looking for, go back all the way back up to the beginning, it says determine the maximum allowable centric compressive load. What is that? That's a force, right? So what I want to do with my critical stress here is turn that critical stress into a force, right? Stress is equal to force over area, which tells me that force is equal to stress times area, right? So F critical is going to be equal to sigma critical, right? 31.057 KSI multiplied by the area of the cross section. What's the area of the cross section? Okay. Yeah, we can go back up here and say it was listed right here, 5.87 square inches. Okay. So I'll put that in right here, 5.87 square inches. And when I do that calculation, what are the units that come out? Yeah, it should be kips, right? Because this is kips per square inch times square inches. So F critical is going to be equal, in this case, to 182.3 kips. And that's a wonderful warm-up, right? Real quick, you know, some of you are kind of getting that stuff probably written down in your notes. Let me go up here, and I wrote a little note up here just to be totally clear. When we see in kind of a typical book problem that we have pinned end conditions, let's say, the way we are going to interpret that for a problem, unless we're given some other kind of information, we're going to interpret that as it is free to rotate in any direction. And therefore, that's what allows us to pick whichever the smallest R value is in the table, okay? You should always be careful on the actual problem you're working to see, is there enough information given that I should question that assumption? Can this thing rotate around one axis but not around another axis? And if that's the case, you might need to do a little bit more in-depth analysis of just which kind of end constraints you're going to have in each direction. You might have to do this analysis twice, is basically what I'm saying, right? Around one axis and then around another axis, and whichever one has a lower critical buckling load, that's what's going to make it fail first, okay? So anyway, just watch the problems that you're given very carefully to see if you might have to analyze them in more than one possible buckling direction. Now, we're going to make this a little bit trickier. What if now, for the same, basic given stuff that we had before, instead of A992 steel, what if we have a, maybe similar kind of steel or another kind of steel here that has a stress strain curve that looks like this one right here? So, basically up to a stress of 36 KSI, that stress of 36 KSI happens at a strain value of 0.0012. And then from there, it kind of changes its slope a little bit, going from there up to 60 KSI. At 60 KSI, we have a strain value of 0.0024, okay? When we have information like this, and we are not given instructions to use like code-based buckling equations, that's a pretty good indicator that what we're supposed to use is the Engesser equation. Now here's the interesting thing about the Engesser equation. In order to actually have the Engesser equation apply in sort of a different area of the curve than the initial linear portion in the elastic phase, right? We're going to have to first figure out where is our load situation going to put us along this curve. It could be that we are down in the elastic range, or it could be that we are up in the range where it goes plastic, right? So we have to kind of try something first and make an initial assumption as to where we are in a problem like this, okay? So what we're going to do in this case is start out by assuming it's elastic, okay? So I'm going to kind of put that up here. Start by assuming that it's elastic. And if I assume it's elastic, what do I get to do here? I get to use the same equation I just did. It's again just the Euler's buckling formula again, right? So critical stress is going to be equal to pi squared times, what's my E value going to be here? Yeah, 36 KSI rise over a run of 0.0012. Remember, the slope in that first little section of the line is the E value, and so I can calculate that E value by just taking the rise over the run. All this over, right, and it says, you know, the other constraint I'm doing here is I'm assuming both ends are pinned. So what does that do with my effective slenderness ratio? Same as before, right? So I can still use 96 in there squared. And once I've entered all this stuff in the equation, I get that this makes my critical buckling stress 32.128 KSI. But again, this is not a critical buckling load. This is a critical buckling stress. If I want the critical buckling load, what I have to do is take the critical buckling stress, 32.128 KSI, and multiply by the cross-sectional area of the member that is carrying the stress, right? And up there a second ago we said that was going to be 5.87 square inches. And what I have that comes out of this equation is going to be 188.589 kips. Now, I kind of skipped right over something that I probably should have mentioned. Okay, so let me go back to it. I said I was going to start by assuming elastic. Okay, how do I know whether or not that assumption was good? Yeah, I need to look at what's this, this stress value that I came up with as a result of making that assumption. What do I need to kind of compare this number with? The strength where that stops being the curve that I'm using, right, which is the yielding strength. You can kind of think of it that way. But, we need to compare these two. If this is less than that, it means that I'm actually along this curve, below that spot, and that tells me this was an appropriate equation for me to use, right? So thumbs up, right? This is our maximum amount of load that we can use, or that we can put on there if this is the stress strain curve. And again, I should probably mention this as well. No factor of safety is built into this at this point, right? So this is literally where we do expect it to buckle, okay? All right, now let's kind of mix this up a little bit. What if it's the same column, but instead of it being pinned, like we just calculated right here, let's do one where we have one end pinned and one end fixed, okay? So if that's the case, then what's my effective slenderness ratio? 0.7 multiplied by the length of 12 feet, which I'm just going to put this in here as 144 inches. That's what 12 feet is. Divided by what? Okay, 1.5 inches was the R value, the radius of gyration that we needed in there. So if I put all this in there, I end up with 67.2 for this effective slenderness ratio. Okay, what else changes? Well, we have a choice at this point. We could either assume that we are still in the elastic range. Does anyone have an inclination as to what that might tell us? Or what we might calculate to if we assume elastic? We were already, when we had a denominator of 96 right here, we were already at 32.128 KSI. I'm suspicious that by changing that denominator up or down to 67.2, it's going to increase that critical stress, right? Probably above that little transition point right there. So this time I am going to try first the plastic portion up here. So what does that mean I need to do? I'm using Engesser's equation here. We're going to have pi squared. Now, here's the only spot where Engesser's equation is different. We need to calculate what is the slope of that chunk of the curve. Well, to do that, we just need to take what's the difference in the vertical coordinate, which is going to be 60 minus 36 KSI, over what? The difference in the strain values, right? Which is going to be 0.0024 minus 0.0012. Okay, and everything that I put in the parentheses right there is the E sub t, right? It's the tangent modulus, because tangent, since this is still just a straight line, the tangent line is the line. So the slope of that line gives us that tangent modulus of the line. Does that make sense? So that's all of that stuff. This is now going to be divided by my effective slenderness ratio of 67.2 squared. Okay? And when we go to put all this stuff in, I get that this calculates out to 43.711 KSI. Okay, so there's that value, and that number, because it is above 36 and below 60 KSI, that tells me that point, lies in there somewhere in that little range of there, and that tells me this was the right equation to use for that purpose. Okay? You want to do one more? What if we have both ends fixed? Okay? So if we have both ends fixed, what does this do to my ESR? Yeah, both ends fixed gives me a K value of 0.5. Okay? So this is going to be 0.5 times the length, 144 inches. Okay, divided by the 1.5 radius of gyration, 1.5 inch radius of gyration. This ends up giving me a value here of 48. Now I don't have any other portion of this thing to use, so I'm going to still assume that I'm in the plastic range right here. And I'm going to write the same kind of equation, right? The critical buckling stress is going to be equal to pi squared times, again we'll use 60 minus 36 KSI, over 0.0024 minus 0.0012. All this now over 48 squared. Now for this one, I end up with here that the critical buckling stress is 85.64 or 674 KSI. Now let me, get a little bit into the weeds here. First of all, let's notice here that number, right? How does it compare with our chart? It's bigger than that, and if you see an X put on one of these charts like this, that's generally an indicator that says, yeah, and it fractured right there. So if the member fractures at 60 KSI, and we're saying the critical buckling load is at 85.674 KSI, what does that tell me in terms of the possibility that it will buckle? It'll fracture before it buckles, right? And so what we conclude there, if what we're trying to determine is how much compressive load can I put on here before we expect failure, that load before we expect failure is going to be equal to just that 60 KSI, not the 85.674, that multiplied by the cross-sectional area, which again was 5.87 inches squared. All right, so this failure force then ultimately becomes, actually I didn't write this one down, so let me put it in here, 60 times 5.87. 352.2 kips. Okay, and I just noticed just now that I never took my last one out to whatever its critical buckling force was. So again, it's the same process, right? 43.711 KSI multiplied by 5.87 square inches. This one gives me 256.584 kips. We having fun yet? Oh yeah. All right. Let's really turn up the fun. We're going to change our thought process now to using code-based equations for this column. Okay? So the column is now composed of A992 steel again, and we're going to be analyzing it using the AISC equations. Okay? And let's do this initially here for the case of both ends of the column being fixed. Okay? What we probably want to do here, first of all, is go back and remind ourselves of the nature of these equations. As a matter of fact, let me go ahead and copy these equations over, or move them over. So here's the equations. We know what our case's effective slenderness ratio is, right? what do we need to know? We need to know this critical effective slenderness ratio so that we know which portion of the curve that we should be trying to use for this part. Okay? So what I'm going to do is calculate that critical ESR ratio, right? So let me do that. ESR sub C is going to be equal to the square root of 2 pi squared, okay? What was the E value of A992 steel? 29 times 10 to the third KSI, right? And what's sigma sub Y? That's the yield strength of this material. This is not a number I would necessarily expect to have you memorize, but if you look that up, it ends up being 50 KSI for the yield strength of this particular A992 steel. Okay, so that means that I can calculate this out. I get that the critical effective slenderness ratio is going to be 106.999. And I'm keeping a lot of decimal places there for a reason. We're going to need to use this number again in a couple of different places, and I don't want to introduce round-off error at this point, so kept a little bit of precision there. All right? So, question is my ESR, my effective slenderness ratio for my case, greater than the critical one? Okay? It is not. So what does that tell me? It tells me I picked the wrong equation here, right? Because this is the equation that is valid if my ESR that I have is greater than the critical one. So what do I need to do? I got to get the big nasty one. Does this actually look as big and nasty as we said a second ago? They still say yes. Okay, well, all right, so let's pull this over. This one applies for our case, so let's go ahead and start populating this equation right here. So the allowable stress that we can have is now going to be equal to 1 minus 48 squared over 2 times the critical one, right? So 2 times 106.999 squared. All this multiplied by what? My yielding strength of 50 KSI. Okay, now in the denominator, 5/3 plus 3/8 times the ratio of the effective slenderness ratio that we have for our case of 48 over the effective slenderness ratio for the critical case, right? So 106, like where it transitions on the graph, 106.999 minus my effective slenderness ratio cubed, right? So 48 cubed over 8 times the critical effective slenderness ratio, 106.999, that value cubed. So literally I'm just plugging and chugging here, okay? And once I have put all this in here, for the case of both ends fixed, it ends up giving me 24.66. This is going to be in KSI, correct? Because that's the only real units that are left over there. So 24.66 KSI. And what do I do with that? I then take that number and I use it to figure out my allowable force, right? And I get that allowable force, by doing 24.66 KSI times, again, my I don't know why I can't remember this number, 5.87 square inches. Okay, and I've got that turns out to be 144.75 KSI. And I want to take a second and comment on this one just a little bit. How does that number compare with, maybe some previous ones that we have done? Like, go back up and think about when we had both ends pinned, right, which is actually less support happening for the column, right? I did that and I came out with a 188.589 kips with less support. That's a bigger amount of, load that hypothetically we could support, right, with less actual support on the end conditions. Yes? Thank you. It's like, so this should be in kips. Sorry about that. But what I was trying to get at there is notice how much smaller this number is. What do you think's going on there?
Factor of safety.
Factor of safety is probably the main answer to that question, right? They've got a factor of safety built in to that design equation. All right, one more to do. What if we have one end fixed, one end free? ESR in this case is going to be equal to what? 2 times 144 inches over 1.5 inches for the radius of gyration. This comes out to be 192. What do I need to do with that? Well, notice here, this value of 192, how does it compare with my critical, the one where I have the transition from one part of the curve to the other? This is greater than, it's also less than 200. Not much, but a little bit less than 200. So that says I'm free to use this equation right here. Okay? So let me grab that equation, pull it down where I can look at it, and populate it. This is going to be 12 times pi squared times E. E is 29 times 10 to the third KSI. All this over 23 times the effective slenderness ratio, 192, that raised to the second power. And I get 4.05 KSI. And what does this give me for my force? 4.05 KSI times the area, 5.87 inches squared. This winds up being 23.779 kips. So we definitely need to be careful with your fixed free end conditions. Okay? All right, so that, we ran through a bunch of different, kind of equations that we can use, all for kind of our standard end conditions. I think we, at one point or another, touched on all 4 of them, our standard end conditions. What we didn't do with this example was anything where we had more complicated, like support schemes to try to figure out, is there other places where the column is constrained from rotation and that kind of thing. So, maybe that will be forthcoming in another example at some point. Any questions? Yes? Well, what example does that physically look like? So let me give you one. What if I had a member that, I'll try to sketch it in 3 dimensions, right? So let's say you've got something that's relatively thin and is being supported with a pin on some kind of a plate. This is a fixed plate right here. And then I've got another fixed plate down here and another pin down here. Okay? So these 2 plates are constraining this thing from rotation, right? And you know that this pin is actually itself being constrained from rotation, right? But the member can rotate around the pin at that location. Okay? So what that means is that this thing is actually free to rotate that way, right? But it is, I would say that way around that axis, right? It is not free, if I made an axis this way, it is not free to rotate around that axis, right? So that means around that, let me change the colors. Around the blue axis right here, since it is not free to rotate, you would have to treat it around that axis as though it was fixed because it's not free to rotate. Around the green axis here, right, it's free to rotate around that axis, so you'd have to treat it like it's pinned, right? Meanwhile, the 2 different directions, just based on how I drew this, it looks like this thing is thinner in this direction than it is in this direction. Agree with that? So that's thinner. And since that's thinner, you're going to have a smaller R value for the axis that runs this way, right? That's going to have a smaller R because it's going to have a smaller I value around that axis. Whereas for this other dimension, that would imply an axis, I'm kind of running out of colors here, but that would imply an axis that kind of went this way, right? And for that axis, you'd end up with a larger radius of gyration. Okay? So what we have here is basically conflicting effects. You have that it is easy, it cannot rotate around the blue axis, that's going to lead to, you know, an increasing amount of buckling load, right? Because it's fixed in that rotation around that direction. But you have a smaller r, so that'll lead to a decreasing amount of buckling load. Here you've got, it can rotate around this axis, that's create a decreasing amount of buckling load, but it's a larger r, so that makes an increasing amount of buckling load. So just by inspection, I can't tell which direction is most likely to buckle. So I have to evaluate both of them and then choose which one is lower. And whichever one's lower is how much it can carry before it buckles. One fixed, one free, that's essentially like a telephone pole, right? So it's like, you know, something embedded, and then you've just put a load on top, but that up there it is completely free to move however it's going to. This is the highest K value, right? This led to a K of equal to 2. And with that, that's what creates, you know, larger effective slenderness ratios, or the kind of the largest K factor that we have for evaluating the effective slenderness ratios. Good questions. Yes, sir. Part 3, this part right here, both ends fixed? Yeah. So on that one, we came up with a critical buckling stress that was higher than the stress where fracture was going to occur. And because of that, you know, because of that, we can't get up to that point. It's not going to buckle before it reaches that point, and therefore we have to cut off when, you know, how much force we apply. We have to cut that off at however much stress the material can actually carry. If I had you know, a lot of things would have to be different, but I think what you're maybe saying is if the numbers had put the point down in here and I had used this equation with that E right there, yeah, it would have been wrong, and I would have had to go back and change and use the E value that was appropriate for that portion of the curve. Is that your question? Cool. All right. Anything else? Okay. Y'all have a good day.